Okay, today's we're going to do exercise 9K, continuity of the function. So let's have a look at this topic here, this exercise. It's not a very hard exercise. You just need to understand the concept that, firstly, a tangent can only be drawn at a point on the curve if. So think about it, all right? Previously, we were always talking about a tangent of the curve. So for example, if we have a curve going this way here, then we can always draw a tangent on the curve that different color, so that we can always draw a tangent. Anyway, don't know how to change the color. Okay, so for example, if there's a point here, if there's a point there, we can actually draw the tangent at this particular point. If there's a point here, we can also draw a tangent as well. Okay, but remember this, we can only draw the tangent if the curve has no break at that point. So it is continuous at this point. Okay, so the curve is continuous. It's a smooth, continuous curve at that point here, so that you can draw a tangent through. Obviously, if it's not a continuous point, you can't draw a tangent because that point does not even exist. And then there is no sharp corner or sharp turning point, there. So it must be a smooth curve at that point. So what does that mean is, for example, you guys all know about the absolute value functions here. So for example, the absolute value function, if we have an absolute value function like this, okay, don't know what's going on. Yep, if we have an absolute value function like this, okay, so the absolute value of something, and then this point here is a sharp turning point or sharp corner here. And in that case, we can't draw a tangent. I know some people would just say, hey, the tangent is just going to be this line here. But unfortunately, it's not really considered that. That's not really a definition of a tangent. A tangent is, a line that touches the curve, touches a smooth curve at only one single point. However, this is not a smooth curve here. It's a sharp turning point. You can also know that it's, you can't really differentiate the absolute value functions here. So for example, if you have an absolute value function y equals to absolute value of x, like very simple absolute value of x, and we have a function like this, all right? And absolute value of x looks like this way here, like that. So you've got a sharp turning point at this point here. And then if the question asks you, hey, differentiate this function, how would you differentiate absolute value of x? All right, I didn't really teach you how to differentiate absolute value of x here. Just because the absolute value of x, you will have two different answers, depends on what is the domain equals to. So the absolute value of x is equal to positive x if x is greater than 0. It is equal to minus x if x is less than 0. And obviously the third option is it can be equal to 0 if x is equal to 0. So you do have different functions, as you can see, plus x, minus x, 0, depends on what is the domain you have for this particular function there. So you can't really differentiate that entire absolute value of x and try to find out what is the gradient of tangent at that particular point here, because it's just not working here. All right, for example, for the function here, the gradient of tangent is going to be just this gradient of this line. However, up to at this point, the gradient of tangent is just going to be the gradient of the line in there. So you can't really do it this way. Okay, so that's one of the things that you need to be careful about. A tangent can only be drawn at a point on the curve if the curve has no break at that point, and also if there's no sharp turning point. Okay, all right. So let's have a look at the next one. All right, so the informal definition, it says a function f(x) is called continuous at x equal to a if the graph y equals fx can be drawn through the point where a without lifting the pencil off the paper. So this is just the informal definition. Okay, so if if there's a break in the curve, then we say this is there is a discontinuity at a point x equal to a. All right, so if you look at this example here, we've got a hyperbola. It's not a continuous function, as you can see. You've got two parts of the function on the left-hand side and right-hand side. So therefore, this function has a discontinuity point when x is equal to 0. And then it's obviously continuous everywhere. Just when x equal to 0 here, there is an asymptote. So it's not really a continuous curve here. So which means like, when you differentiate it, you are going to get, you're not going to be able to differentiate when x is equal to 0. So if you try to differentiate y equals to 1 over x, think about this method here. The derivative is minus x minus 2. Then if we substitute x equal to 0 inside, it is going to be undefined because we can't have a denominator equals to a 0. So that's why we can't differentiate that function when x is equal to 0. So this is the concept we're going to study in the next exercise. All right, but these two exercises are sort of like related to each other as well. Okay, so if you look at the second diagram here, it's a parabola, and this parabola is continuous for all the values of x. No matter where's the x, all right, it is always a continuous curve, so therefore you can differentiate and you can find the gradient of tangent at any point on the curve here. So anywhere on the curve, you can find the gradient of tangent. All right, so tangent is going to be here, tangent is there. Even at this point here, it's a smooth curve here, so therefore you can find a gradient of tangent, and then it's going to be horizontal. The tangent is just a x-axis. All right, next one, this is also discontinuous. We've got two discontinuous points. The first point is when x is equal to minus 1. Second is when x equal to 1. Okay, and apart from these 2 points, everywhere else, the curve is actually continuous. All right, so that means when you actually differentiate this function here, you're not going to find the gradient of tangent at these 2 particular points. You're just going to find out that when x is equal to plus minus 1 here, then you're going to get the result it's undefined when you try to find what is the derivative of the function at these 2 points. Okay, so this is what just an examples wanted to tell you. All right, so the next information that you need to know for this exercise is the piecewise defined functions. So like what I did before about the absolute value functions here, so I break this one down into like 3 parts, as you can see, 1, 2, and 3, depends on different domain of the function you have here, and we can call this kind of function is a piecewise functions. Now sometimes a piecewise function is a continuous function, sometimes it is not. So what you need to do is you just need to be able to draw the function based on what the domain they give it to you. So let's just have a look at the example they give us here. All right, and I'm just going to use the method to actually show you how to actually sketch the piecewise function. So we have first example here is a piecewise function. Oops. Okay, piecewise defined functions. All right, so if we just use the first example they give us here, fx is equal to, it's breakdown into 2 parts, 4 minus x squared and 4 plus x. This is for x that's less than or equal to 0, and that's for x that's greater than 0. All right, so how would you draw this function here? I know that, as you can see, different domains here, you have a different function. That is a quadratic, which is a parabola, and this is a straight line. The best way or the easiest method to draw a function like this is you actually draw the entire function. This is what I feel like, that's the best way of doing it. You draw the entire function. Okay. To try to find a good line. Right, so you just draw an entire function. For example, I want to sketch fx equals to 4 minus x squared. Don't worry about this domain right now. Just don't worry about it. You draw the function here. Okay, so the function can be drawn, and this is like, what's I call it? It's a parabola that's concave downwards. The y-intercept is 4, x-intercept is minus 2 and 2. So you've got a function like this. It's a parabola. Okay, all right, and that parabola is concave downwards. Okay, so once you finish that, then you start to look at the domain of the function. Okay, so this function only works when x is less than or equal to 0. So in that case, what does that mean is you need to remove the part that's greater than or equals to 0. So I need to remove this part here. You don't need that part, right? So you need to get rid of, use your pen, rubber to get rid of this part. I know sometimes the student will say, hey, what's the point, all right, to draw this one in the first place, even you know that x is less than or equal to 0. Now remember this question is an easy question. It's for x less than or equals to 0. Sometimes they give you other random numbers. Instead of 0 here, they can give you like a 5 or 2 or 2.5. And in that case, if you don't draw the entire function, it is going to be very hard to identify where is the location of 2.5 for the x values. So therefore, you have a different y values. So if you draw the entire function, then you can always cut the functions if you need. All right? Does that make sense? Okay, so now what I'm going to do is just remove the part here. We don't need this part, all right? This part does not belong to the function. That's all, okay? So, and I need to draw a little, like, solid point at 1x equal to 0. Because when x equal to 0, it still belongs to the first function there. All right, so once this is done, then we can move on to the next one, x plus 4. Okay, for the x plus 4, it's a straight line, okay? So for example, you can just pick another point that you want to do. So when x is equal to 1 here, y is equal to, for example, that's equal to 5 there. Okay, I didn't do that, that's a scale diagram, but anyway. So we've got 5, and then you can draw a straight line through this point. Oh, what am I doing here? Okay, through this point. Okay. Yeah, that looks pretty good. All right, and that becomes a straight line. Okay, please also put arrows on both sides of this function here. All right, so that becomes the function. It is a continuous function, as you can see, but is this a smooth continuous function? Not really, because we have a sort of like a sharp turning point or sharp points here. Okay, but this is a function. It's a continuous function. Okay, so hopefully you can actually see there's a sharp point that is actually turned. Okay, so around this point here, when x is equal to 0, for example, you can't really differentiate it. Okay. Because actually with this point here, also this is a sharp point, but then when x is equal to 0, you do know the domain belongs to the first function, which is y equals to 4 minus x squared. So in that case, yes, it is still possible to differentiate at x equal to 0, but you're going to choose that function to differentiate instead of this function here. Okay, does that make sense? As you can see, the textbook didn't really emphasize about, when x is equal to 0, there is no point for the second function. So it's a bit tricky for a question like this. The way I usually do a question like that is, I know sometimes the textbook, they don't really emphasize it. As you can see, when x equal to 0, it only belongs to the first function, not the second one. So therefore, for the second function here, I was a bit picky on these kind of things. All right, I will actually draw an open circle like this, where the second function only touches the outside of this open circle, which tells me or indicate to the teacher that the second function, when x equal to 0, there is no value for y. Okay. However, what's inside here, as you can see, I put an inside part here, it belongs to the first function. Does that make sense? All right, the outside where it is just an open circle or empty circle, and then this line or this second curve or function only touches the outside of that. But it looks like the textbook didn't emphasize this. Okay, so either way, I guess you can do it. I hope that you can sort of remember the way I do it. It just makes more sense, all right, if you do it this way. All right, this is what a piecewise function is. Remember, not every piecewise function is a continuous function. You can have a piecewise function that's not continuous at all. So like in this, the next example here, this is also a piecewise function. However, they are not continuous function, as you can see. It's broken down into 3 parts. When x is less than 1, you've got exponential growth function there. When x equal to 0, you just have a point. When x equal to 1, you just have a point, which is that point there. Okay, this point here. And then when x is greater than 1, you've got y equals to x squared, which is just a parabola. Okay, again, to sketch the function, we're still using the same method like what we did before. We sketch function one by one, and then we remove the part that's not in the domain, and we connect the points if we can. We remove the point, or we change the points into the open circle or empty circle, depends on what the domain is, and then you should be able to do the question without any major issues here. Okay. All right. Yep, I think they mentioned something about open and closed circles, all right, and arrows. A closed circle makes an endpoint that is included in the graph, and an open circle marks with an endpoint that's not included in the graph, and then an arrow marks, marks the curve that continues forever. So we've done this before, all right, which is very similar. Okay, so the next sort of concept that you need to understand is we can have a function which numerators and denominators have the same zeros, and this is becomes a bit tricky, so I'd like to show you an example. So that's a good example, but I do want to show you slightly different examples here. So I think I mentioned that before, previously, about that function in which the denominator and numerator have the same zeros. Okay. All right, and you should be able to recognize this question when I show you the examples here. Okay, so this is I think I'll show you like a one way of dealing with, sketching the functions here. So it's like, I think I did this kind of things, all right? So y equals to x squared over x, this kind of things. All right, and I'll ask you to actually sketch the function. Now remember, I told you this is very important, because if you try to use your algebra to simplify this function before you sketch, obviously that you get y equals to x. However, during the process of this algebra manipulation, the domain has changed. Okay, for the previous function, domain has changed. For the previous function, the domain of the function is all real. Okay, all real value of x except x equals to 0. So you can't have x equal to 0. However, the domain of this function here is just all real x. Right? There is no denominator, so you don't have any problem of letting x equal to 0. But unfortunately, when x is equal to 0, it does not work for the original function. Remember, we are still sketching the original function. Okay? So in that case, what we are going to do when we're sketching this function here is, I know like we do sketch the function, it's y equals to x after we simplify it. But then it's super important that we need to remove the point. So this is just a straight line of y equals to x. Okay, and so I can label this as y equal to x. However, if you want to sketch y equal to x squared over x, in that case, is you're going to remove the point here. That's a bit too big, okay? You're going to remove the point here when x is equal to 0, the function is undefined. All right, so this is what happens is when we have a function in which the numerator and denominator have the same zeros. Okay, I forgot to write this, have the same zeros. Okay, looks a bit ugly, sorry. Okay, so if you look at an example, they provide you here fx is equal to 3x plus 3 over x plus 1. Well, same thing happens, because what you can do is you can factorize the numerator, and then you can cancel the denominators, all right? Because they do have the same zeros when x is equal to minus 1. Okay, so you end up with 3. So that means when you actually sketch the function, it's just going to be a horizontal line when y is equal to 3. However, you need to remove the point, because according to the original function, the domain is x not equal to -1 here. So you can't have x equal to -1. So that means when you sketch this function here, when x is equal to -1, you need to remove that point by changing this point to an open circle. Okay, and this is what they have done here for the function. So this is extremely important, and sometimes the student get confused about, they just they simplify the function because they need to sketch the function. However, they totally forget about, after you simplify the function using algebra, sometimes some important information like domain and range sort of lost or got changed through the process. So that's very important when you actually simplify any function from the original function, and then you start to sketch. All right, you need to pay attention to the original domain and the original the range, and then decide whether you need to remove the points or not. Okay. So I guess apart from that, that's all for this exercise. It's actually pretty easy here. To be honest, like I don't think I need to do any of the example questions. They are straightforward. You guys can actually try to do this, the questions there. Overall, this entire exercise just introduced about the concept of what is the continuity at a point, what is meant by the smooth curve, and then in the next exercise, we're going to talk about differentiability. Okay? All right, thanks for watching.